Today we're going to discuss and start out with our nuclear chemistry. So we're going to combine this with bonding. So nuclear chemistry, we're going to talk today about some basic ideas of nuclear chemistry. So our learning target is to describe a stable isotope. How are we going to get to that learning target? Well, our success criteria are two. Define an atomic mass unit. Now, if you look up here, AMU or U, I've seen this abbreviated both ways, okay? I'll talk about it both ways. So you need to know whether I say an AMU or just a U, that we are discussing the atomic mass unit. We also need to be able to describe the strong force that is exerted by nucleons. This is the first time we've been introduced to the word nucleons, so we'll discuss that here in a bit. We need to identify that protons and neutrons are made up of smaller particles that we call quarks. We need to relate how energy and mass can be interconverted using Einstein's formula there, E equals mc squared. And finally, we need to be able to predict the nuclear stability of an atom. We're just going to review some stuff that we know about the nucleus. Okay? The nucleus is composed of nucleons. So here's that new word, a nucleon. What is a nucleon? Simply, it's referring to protons and neutrons. When we talked about the nucleus previously, we said we had an atomic mass number. That atomic mass number is actually the number of nucleons because it's protons and neutrons together. So the atomic mass number is the number of nucleons. The atomic number, we represented Z, is the number of protons. So when I bring up this diagram here, the element is letter X, the symbol for the element. Okay? The number of nucleons right here is A. The atomic number, which is the number of protons, is Z. So when we look at a specific one of these, aluminum here, okay? Aluminum has 27 nucleons, 13 protons. Well, when I can do my math, I'm pretty good at that, okay? 27 nucleons, 13 protons, that leaves me with 14 neutrons, correct? That stuff all should be reviewed for us, other than the word nucleons. Now, when we go through and we look, a subatomic particle, okay, we broke down the atom. We said atoms are made up of subatomic particles. In the nucleus, we have protons and neutrons. And around the nucleus, on the electron clouds, we have electrons. Now, we talked about this before, but here are the masses. 1.0073 atomic mass units for a proton, 1.0087 atomic mass units for a neutron, and look right here, 5.485 times 10 to the negative fourth atomic mass units. So we described before that in terms of weight, the electron was very, very negligible. It was so small that we didn't even usually count it in terms of the mass of an atom. These kilograms here are what the actual masses are. So those are all, you can see, negative 31, negative 27, negative 27. They're very, very small in terms of kilograms. But this atomic mass unit right here is going to come and play in a little bit here, these values. Now, a strong force, ladies and gentlemen, a strong force. Excuse me. Hideki Yukawa, 1935, he said that there is a force that exists in the nucleus, okay, that is even stronger than the electrostatic repulsion. Now, we know that opposites attract, likes repel, correct? So how then, when I look at this picture, how are all these pluses so close together? Shouldn't they be repelling each other? Absolutely. Well, Yukawa proposed that there is a force that is greater than that repulsion force. Okay? Later research showed that not only between two protons, but there's also this force between two neutrons, and there's also this force between a proton and a neutron. So everything, this strong force, is dealing with everything in the nucleus, and that's what's holding it together. Okay? And I just let the cat out of the bag. He named it the strong force. So he said that there's this force that is stronger than the electrostatic repulsion. Now, just a little bit, we're going to not hit on this too hard, but the strong force is created by the nucleons exchanging particles called mesons. This only happens when the nucleons are very close together. So what no, not so much the mesons, but look, these are really close together, aren't they? So they would be able to exchange these mesons. Now over here, this plus is pretty far from that plus, isn't it? So they wouldn't be able to exchange them. So those wouldn't have the strong force. It's only when they are very, very close together. So if we look at this right here, yes, they're pretty close together. These two neutrons are pretty close together. This neutron and that proton, they're pretty close together. So they would be exchanging those mesons and having the strong force. But there wouldn't necessarily be strong forces between the ones that are further apart, just the ones that are relatively close. Now this diagram here I thought it was kind of interesting because protons and neutrons are made up of smaller particles that we call the quarks. So we started off saying way back when that atoms were the smallest thing, okay? Atoms were the smallest thing that existed. Well, then we found out that there was a nucleus, which was even smaller than the atom. Remember who? Who's the guy we talked about did the nucleus, Stephen? Rutherford. And what was his experiment that he did? Carly? The gold foil experiment, okay? Rutherford founded the nucleus by blasting alpha particles at gold foil. And remember the ricochets, and sometimes it passed right through. So there we got the nucleus. Well, pretty soon then we said, wait a second here. This nucleus is made up of nucleons. It's made up of subatomic particles, made up of protons and neutrons, correct? Well, then we said, wait a second. Those protons and neutrons are made up of things, right? Those protons and neutrons are made up of what we call quarks. Up here is a neutron. So this blue ball right here is a neutron, and we can see the little red, the green, and that's kind of a grayish right there. So those are quarks that make up this neutron. Now, here are the quarks. There are 6 different quarks. And you don't need to know this, but I'm just going to tell you. Here's the unique and creative names that they gave these quarks. Up, down. Charm, strange. Top, bottom. Okay, pretty creative names, aren't they, for quarks? So, these quarks make up the protons and neutrons. Now, this is just, what do you think? Do you think in the future that we could possibly find that quarks are made up out of something? Yeah, the way everything's rolling. I mean, look right here at 1910, and then we're up to 1980. So, yeah, that's possible. That's possible. Mass defect. Okay, we're going to talk about the mass of a nucleus. Okay, carbon-12 has a mass of 12.000 atm. Now, its nucleus contains 12 nucleons, 6 protons, 6 neutrons. Each nucleon has a mass a little bit over 1 AMU. Okay? If I remember right, one of them was 1.0087. Okay? So it's just a slight bit above 1. So, if the mass of the nucleus is slightly less than the mass of the individual nucleons, all right? So there's a little bit of mass that is not accounted for, okay? That missing mass is called the mass defect, okay? Delta M, the mass defect, delta M, is equal to the mass of the nucleons minus the mass of the nucleus. So I'm going to show you this here, this mass defect. We said that carbon-12 has 6 protons. Each proton has a mass of 1.0073, so that gives me a value of 6.0438 atomic mass units. We did the same thing with neutrons and their mass, okay, which that is not correct there. That is not correct there, because a neutron is what, 8.7? Is that what I said? I believe it's 8.7. So what I'm going to do here, all right, here we go again. Now I have that corrected, okay? Now I have that corrected to give the correct value. The 6 neutrons times 1.0087 gives me 6.0522. So when I added those together, the total nucleons came up to 12.0960. However, I told you before that this mass defect was the mass of the nucleons minus the mass of the nucleus. So I take that mass of the nucleons, and I told you that carbon-12 had a mass of 12.000 AMUs. So I come up with a value, my mass defect is 0.096 AMUs. It's pretty small, isn't it? That's a pretty small number. So that mass defect is not huge. But where does it come from? Okay? Where does it come from? Well, in Einstein's equation, mass and energy can be interconverted. So E equals mc squared. Energy is equal to mass. Anybody remember what c squared was? Yeah. The speed of light. Okay? So energy equals mass times the speed of light squared. When protons and neutrons are packed together to form a nucleus, some of the mass is converted to energy and released. This amount of mass is equal to the force of the attraction holding the nucleons together. That strong force. Okay? So that strong force is where we get that extra mass. Okay? So if we think about it, a very small quantity of mass is converted into an enormous quantity of energy. Why? Well, think about it. The speed of light is approximately 300 million meters per second. That's a pretty big number, isn't it? So, when I look at this whole energy bit, a small amount of energy can convert into, or excuse me, a small amount of mass can convert into a huge amount of energy. Well, let's stop and let's throw into this E equals mc squared. We just said that I had 0.96 atomic mass units. That was my mass defect, right? I take that and I multiply that. I got this off of the internet, the speed of light, exactly that the internet gave me. 299,792,458 meters per second. And I square that value. When I do all that math, it gives me energy of 8.6 times 10 to the 15 joules. So even though there's a teensy bit of mass, there's a heck of a lot of energy. Okay? That's going to come into play later on when we talk about nuclear energy. All right? Final thing we're going to talk about today is the whole idea of nuclear stability. Okay? And it has to do with how many neutrons. We discussed when we talked about isotopes earlier that an isotope of an element had the same amount of protons, different amounts of neutrons. Remember our discussion of carbon-12 versus carbon-14. All right? So the number of neutrons in a nucleus can vary. The relative degree of stability is created by having too much or too few. I should say the degree of instability. Okay? When the element is unstable, it's because there are either too many neutrons or too few neutrons. Stable nuclei do not decay spontaneously. Okay? Unstable nuclei have a very certain probability to decay. So how do we know whether something is stable or something is unstable? Well, one way to predict the stability of a nucleus is to compare the number of neutrons with the number of protons. All stable nuclei are shown as red dots. If you look at this, all of these red dots running all the way up here, those are the stable nuclei. All right? So, we call this the band of stability or the belt of stability. This little red line here is 1-to-1 proton ratio. Okay? Proton to neutron ratio. So, if I look at this 1-to-1 ratio is what this red line is, I said. I look at this. For elements that have small atomic numbers, the most stable nuclei are those in which the neutrons and the protons, when they come up together with a 1-to-1 ratio. For elements that have larger atomic numbers, the most stable nuclei is when that ratio is 1.5 to 1. So if I look at this down here, right here, you probably can't read it, but this is element 20 and below, because these are the number of protons right here. Okay? Or actually, these are the number of neutrons. These are the number of protons. Okay? So right here is 20. 20 and below, can you see that's right on that 1-to-1 line? Okay? That's right on that 1-to-1 line. Those are stable nuclei at that point. Okay? Right here is ZR, which is zirconium. Zirconium right there has a 1.25 to 1 ratio. So it's a little bit over the 1-to-1 ratio. Right here is tin. Tin is a 1.4 to 1 ratio. Right up here is mercury. Mercury is a 1.5 to 1 ratio. Okay, so the bigger elements are stable at a 1.5 to 1 ratio. The smaller elements are stable at more of a 1-to-1 ratio. That's just a generalization. It's not an exact science. Okay. So when I look at this, carbon-12 has 12 nucleons, 6 protons, 6 neutrons, gives me a 1-to-1 ratio. Would you consider carbon a smaller element or a bigger one? It's a smaller one. Yeah. So is that 1-to-1 ratio going to say it's pretty stable? Okay. Now let's look at carbon-14. See how its ratio now is 1.33 to 1? Okay, so carbon-14 is not going to be very stable because it's not at that 1 to 1 ratio. Okay, so if it's not very stable, it will decay. Okay, it'll undergo nuclear decay. Here's another we're gonna look at. Let me spit that out. Here's another one we're gonna look at. Mercury 2O2. So it has 202 nucleons. I know that mercury on the periodic table has atomic number of 80. Okay, so that means 80 protons, 122 neutrons. Okay, would you consider mercury a bigger or a smaller element? It's a bigger element. So does that 1.52 ratio to 1 ratio make sense on it being stable? Absolutely. Now here's another mercury, mercury 80. Okay, so it has a very, very different amount of protons. So, or excuse me, of neutrons. Got to have the same protons to be mercury. Has a different amount of neutrons. So the 180 nucleons minus the 80 protons gives me 100 neutrons. The ratio of neutrons is 1.25 to 1. Neutrons to protons. That's somewhat under the 1.5 to 1, isn't it? So what do you think? Do you think that's going to be stable? No. No, it's going to have some nuclear decay. Okay, it's going to have some nuclear decay going on. All right. So folks, this is just an introduction to what we're going to be talking about with nuclear chemistry. Okay. So probably the biggest thing is to remember that ratio of neutrons to protons and how it affects the stability of the nucleus.